Hey everyone. In this episode of ITS Now, it's the second part of our Traffic Signals Principles series. If you missed part one, which was on phases and stages, I'll put the links down below. In this one, we're looking at the interstage period, so it's intergreens, conflicts, etc. Really fundamental to the safe operation of traffic signals here in the UK. So really important to understand what's going on. Anyway, I'm Alistair, and this is ITS Now. When designing a traffic signal installation, each assigned phase is assessed to ascertain if its traffic movement would impact with the traffic movements of each of the other phases, if they were to operate at the same time, even if it's intended that they never do so. These are referred to as conflicts. It should be noted that if a pair of phases is found to be conflicting, say phase A to E, then the reverse pairing, therefore phase E to A, would also be a conflict. A conflict matrix is programmed into the traffic signal controller, or TSC for short, to reflect all of the possible conflicts. In this simple example, you can see that the conflicts above the diagonal line are symmetrical with those below it. The TSC contains a safety monitoring system, and in the event that the two conflicting phases were to be active at the same time, this would automatically shut the TSC down. This is the most critical safety feature within a TSC, which once programmed cannot be overridden, either locally or via the UTC system. So this Italian job scenario just wouldn't be possible to force conflicting phases to operate at the same time. The period of time between specific phases being active, so that's from the green on one phase extinguishing to a green on a conflicting phase illuminating, is called the intergreen. Each conflicting set of phases will be programmed with individual timings, which are used to provide a minimum period of time between their activity. Although the values of each intergreen timing can be altered within the TSC, there is a minimum limit value that stops these being changed accidentally or maliciously to an unsuitably short period of time. As with the conflict matrix, this is an important safety period, therefore cannot be circumvented in operation. The intergreen, therefore, ensures that the flow of traffic from the terminating phase has passed before the subsequent phase starts to move. By default, there will be a 5-second intergreen between conflicting phases caused by the leaving and starting amber periods, which are 3 and 2 seconds respectively. These relevant phases, referred to as sequent ambers. We'll look at the issues associated with the intergreens from vehicular phases to pedestrian phases a bit further on. However, it may be found that the required period of separation between specific phases will need to be longer than this to account for the geometric design of the junction. With the distance between each phase being of paramount importance, along with peripheral issues such as the topography of the junction also requiring consideration. Longer intergreen periods are achieved by running the red aspect of the appropriate phases between the leaving amber and starting amber periods of the respective phases. If the intergreen is set too low, it could result in two sets of traffic flows colliding. If it is set too high, it will adversely affect the capacity of the junction and result in traffic congestion. So how do we calculate intergreen timings? The value of the individual intergreen timings for all conflicting phases are calculated by determining the transit times to the probable collision points between each conflicting phase. Although these timings can be determined using modeling programs, because of the safety critical nature of these, it is recommended that these are calculated manually to ensure the safety of the installation. These can then be compared with the model outputs to ascertain if any conflicts have been missed or timing values need to be examined further. To undertake the manual calculation, a scale drawing of the signalized junction design is used to establish the swept paths for each traffic movement, and then to determine the location of each of these collision points. The distance for the phase losing right-of-way is measured along the center of each swept path from the relevant stop line to the collision point, and then for the phase gaining right-of-way from its stop line to the collision point. The intergreen period is calculated by subtracting the distance for the phase gaining from the phase losing right-of-way, which gives what is referred to as the X distance. On approaches with multiple lanes, measure all the available transit paths and always use the longest distance to calculate the X distance. Once the longest X distances are established, refer to the intergreen table to find the required intergreen periods. See section 6.6 of my traffic control book. There is a link in the details below. Or look at table 6.1 in chapter 6 of the Traffic Science Manual. It should be noted that it is essential to ensure that the X distance and resulting intergreen timing is calculated in both directions for each pair of conflicting phases, because the required timing can be markedly different. So, some thoughts about how to use this table to establish robust intergreen values. Although the minimum permissible intergreen period in the UK is actually 4 seconds, where the leaving and starting amber periods of the opposing phases overlap by 1 second, the minimum period given in the intergreen table is 5 seconds. In fact, in some situations, the intergreen value may be lower than this, such as an indicative right turn arrow in an early cutoff sequence could be as low as 3 seconds, or to or from a dummy phase can be 0 seconds. In the event that the X distance calculated is a negative number or is less than 10 meters in distance, an intergreen period of 5 seconds would normally be used. To achieve longer intergreen periods in excess of 5 seconds, instead of using variable amber periods as are used elsewhere, the red aspects will be displayed between the leaving and starting ambers of the respective phases. An additional period of 1 or 2 seconds may also have to be added to the given figure to account for sight conditions. This may include where vehicle speeds on the phase losing right-of-way are considerably lower than those on the phase gaining right-of-way, which may be caused by a turning movement, an uphill approach to the junction for the phase losing, awkward geometry of the approach, or could be caused by the mix of vehicles using a particular approach, such as high proportions of HGVs or agricultural vehicles. Until it was superseded in 2006 by the current intergreen table, the previous version included additional entries to account for these. However, the multiples which we used were not consistent for the amount of additional intergreen period added for longer X distances. This does, though, highlight the need for careful consideration to be given to the specification of intergreen times, especially when they relate to problematic approaches.
Please subscribe to keep up to date with ITS Now.
The original 1966 Webster and Cobb intergreen example diagram still forms the basis of current advice on determining the relevant intergreen durations. So to establish the intergreen from the eastbound traffic to southbound traffic, phases A to B, measure the distance from A to F, then subtract the distance B to F to find the X distance. Then use the intergreen table to determine the base timing. So we'll do an example for A to B. This would be 17 meters from A to F minus 6.5 meters B to F. So that equals an x distance of 10.5 meters. Therefore, the intergreen would be 6 seconds. And the reverse intergreen, B to A, would be 6.5 meters minus 17 meters, equals an x distance of minus 10.5 meters. So the minimum 5-second intergreen would be selected. So the value of the two intergreens in this pair are different because of the difference in the relative distance from each stop line to the collision point in the conflict zone of the junction. There are software tools which can be used to determine intergreens. However, it is important that users understand these principles before attempting to use those. As well as vehicular intergreens, we also need to ensure that other traffic modes are also accounted for. So the first of these that we'll look at are cyclists to vehicle intergreens. At signalised junctions, the vehicular phase timings may need to be reviewed to also account for cycle requirements, because cycles take longer to accelerate from a standing start, are normally substantially slower than motorised vehicles, and their performance is severely impacted by uphill gradients. These issues should also be considered at junctions used by cyclists. Of particular importance is the ability of cyclists to clear the conflict zone. So that's the area in the centre of the junction prior to other traffic movements reaching it. This will be particularly important at larger sites which have a greater journey time for cyclists to clear the junction. Use this intergreen table for cycle phases. It's in section 12.2 of the Traffic Control Book. The next two issues we'll look at are for pedestrian phases. Firstly, we'll look at vehicle to pedestrian intergreens. For calculating the intergreen period from a vehicle phase to a pedestrian phase, measure the distance from the vehicle stop line to the pedestrian crossing stud line on the far side of the crossing from the approaching vehicular traffic. This allows the vehicles to clear the pedestrian crossing before the conflicting pedestrian flows start. The measured distance is the x distance, and the intergreen should be implemented in reference to the intergreen table in section 6.6. For the resulting intergreen period, it is important to make allowance for slow-moving traffic, such as turning movements, to clear the crossing location. So this may require an additional period to be added. And then the reverse of this is for pedestrian to traffic intergreens. The intergreen period between a pedestrian phase and a subsequent vehicle phase is particularly important to ensure the safety of vulnerable road users by allowing them to clear the crossing before vehicles gain right of way. Instead of using an x distance, the intergreen period is based on the crossing distance over the carriageway, curb face to curb face, and then using the average walking speed to calculate how long an average pedestrian should take to cross. Where an individual pedestrian phase is used to control more than one crossing point, the longest crossing distance should be used for the calculation. The crossing distance is divided by the pedestrian walking speed to give the crossing time. Pedestrians are assumed to walk at an average speed of 1.2 meters per second, although to allow users with less mobility, a figure of 1 meter per second is widely used for this calculation. It should be noted that some mobility studies have found that a figure of 0.8 meters per second may be more appropriate for those users who are at the least capable end of the mobility spectrum. Alternative pedestrian walking speeds should therefore be considered when designing a signalised crossing facility, especially where there may be a preponderance of less mobile users, such as near to residential areas or close to hospitals or schools. The final figure is also commonly increased by 2 seconds and rounded up to the next whole second to add a comfort factor for users. Best practice for signalised crossings is to use pedestrian on-crossing detection to allow for clearance period to automatically extend to provide a safer crossing for mobility impaired users. We will look at this subject in more detail in a later episode of this series. Once installed, it is essential that the operation of a signal installation is validated, and part of this process should concentrate on assessing the appropriateness of the intergreen values to reflect on site observations of typical driver behaviour. If there is concern that any intergreens have been set too low, these can be increased by handset command on site to temporarily improve safety. However, these should be formally reassessed and reprogrammed into the TSC configuration to ensure that they are not inadvertently reduced to the original value at some point in the future. In the event that intergreens are set too high, these will not pose a serious safety issue, but will affect the efficiency of the signals. Because of their critical safety role, the ability to reduce intergreen values by handset command are normally blocked or limited to -1 second. But this is dependent on the Highway Authority procedures. It will therefore be likely that the TSC configuration will need to be updated, but it is essential to formally reassess these timings to ensure that an intergreen period is not reduced too far so that it then becomes dangerous. The period between a stage ending and the next stage starting is called the interstage period. The interstage period starts when the first phase green aspect extinguishes in a stage and finishes when all the constituent phases start to display the green aspect in the subsequent stage. The duration of the interstage period will be governed by the individual intergreen timings for all constituent phases in the two stages. But in addition, phase delays are sometimes used, which if present, will also extend the interstage period. Phase delays can be used for both phases losing or gaining right-of-way. The phase delay is specified on a particular stage-to-stage movement, so it doesn't have to operate on all movements to or from the associated phase. Typical uses include extending a phase green period to increase traffic throughput, or to delay a phase starting to allow an opposing phase to establish itself to block right-turning traffic at the start of a stage. The advantage of a phase delay is that because it is specific to a particular stage change, it won't unnecessarily increase the interstage period for other stage movements, so will minimize the impact on efficiency overall. During the design of a set of traffic signals, as well as considering the phase stage arrangements to be used, the interstage consequences of the stage arrangements also need to be thought through. This will reveal any particularly long intergreen times between specific phase combinations are unduly affecting the efficiency of the junction by introducing excessive wasted time to the cycle. It may be possible to review the phase stage arrangements to reduce the likelihood of that particular phase combination appearing in subsequent stages. So, the terms you've learnt about in this episode are conflicts, intergreens, sequent ambers, X-distance, interstage period, and phase delays. So when you're designing a signal installation, defining the conflicts and setting the appropriate intergreen timings that are appropriate for that specific site is absolutely fundamental to the safe operation of that installation ongoing. So it's really important that the designer understands those issues and takes the time to undertake that aspect of the design and specification process properly. If you want to find out more about how traffic signals work, have a look at my two books, Traffic Signals, which is an introduction to the subject, and Traffic Control, which is a bit more detailed and in-depth. Both of these are available from Amazon, or have a look on itsnow.org for more details and links. Lastly, could you please subscribe to our channel? If you've done so already, massive thank you for that. Really does help us and our ability to bring you future episodes. Quite a few of you are watching without subscribing, so please just click on that button. It will be really good. Thank you. Anyway, thanks for watching. See you next time.